So we're going to move on to our first panel discussion. Thanks again, Roger, for joining, and go ahead and turn it over to APL's LSIC director, Jamie Porter, to moderate our ISS and NASA Heritage panel.
All right, guys. Hi, I'm Jamie Porter, our new director. I keep saying new. I'm going to keep claiming I'm new until someone tells me I can't get away with saying that anymore. I don't want to keep you from your coffee, so we're going to jump right in because I know I'm right before the coffee. How we're going to do this is I am going to do like a brief introduction to our speakers, and they're going to go through their slides or no slides. We kind of have a mix of both. And then after that, we're going to take questions. We do want to take a large chunk, maybe 20 minutes of this session to get to your questions. So go ahead and put those in the Q&A as you come up with them, but we'll wait till everyone goes to get to those questions. So, okay, we're going to start with Jim Soder. And let me talk a little bit about Jim. Jim is retired from Glenn Research Center in Cleveland, Ohio, with 46 years of NASA service as a senior technologist for power. Prior to his retirement, he served as chief technologist for the area of intelligent modular power systems, as well as a SME for power supporting NASA's Gateway program. Prior to that assignment, he was chief of power systems development branch for directing advanced power component and power system technology developments for the ISS program. Jim was instrumental in the development of the end-to-end power system verification strategy, development of on-orbit assembly hardware, as well as design and build up of advanced technology hardware to support programmatic risk reduction. And he's a lifetime member of IEEE and they're receiving numerous awards through the NASA Exceptional Service Medal. I think I see Jim. Jim, are you ready?
Can you hear me?
Oh, I can hear you.
Okay, let's see. Let me try to get the
Get your slides up.
the slides up real quick.
Okay.
Okay. Do you see them?
I don't. Not yet.
You don't. Oh.
I have your slides queued up too, Jim, if you'd like me to just go ahead and share and drive.
I can, when you share, do you hit share screen?
Yes, you hit share screen and then you can share that application of your slides.
Okay, I just hit the shared screen.
Does a window
it says select the window you want.
Yes.
Woo. Which one do I want?
Look at the windows.
Okay, I got it. All right.
Got it?
How's that?
It's thinking about it. Now we're cooking with gas. Okay, there we go.
Okay, well, let me go back to the beginning. Okay. All right, well, we got that straightened out. Okay, so I told Matt I'd do about 9 minutes on this. So basically he asked me to address ISS development reliability pretty much from a historical perspective. So that's what I'm going to do. And the historical perspective basically starts in the 1980s. Just as a note, I have quite a few slides, and I'm just going to hit everything at a treetop level. So hopefully, if something strikes your fancy, you can basically take and ask me later on in the discussion. Okay, so what I'd like to do is to hit 4 things: the space station power system overview, which probably a lot of you are familiar with. There were quite a few power system design challenges for space station. Talk a little bit about what we did for reliability there, and just have some takeaways at the end. As I say, pretty much everybody knows what the space station is. I think it's really it's the largest power system I think that we've flown to date. It actually has 240 kilowatts of solar power available if you could get all the arrays up there at the beginning of life. It's energy storage. It has 24 batteries. Initially, they were nickel hydrogen. Now they've been upgraded to lithium ion. And the power distribution level that you get to the users is about 75 kilowatts. That's I believe in the U.S. segment. There was in the 80s, nobody talked about a Russian segment, but there's 8 power channels in there, and I'll talk a little bit about that real quick later or in the next slide. The distribution voltage you have on the primaries is fairly unregulated. It goes from 116 to 170, or can go that high, but the secondary is very regulated at 120. This is a simplified schematic of the primary power system on the station. And what I wanted to point out here is that you have basically 8 different power channels on there, which I'll show you in a little more detail on the next slide what those consist of. But you have 8 different channels which are interconnected through a switching network. The key thing on these power channels is it's not possible to parallel them on a primary. So you have really a channelized system, which does 2 things. One is you have a lot of redundancy in a system like that, because if you lose one channel, it's pretty much isolated from the other one. But the big problem, of course, is that you have a lot of breakage, because you can't completely load one channel up. You can't completely load all the channels up to full power at any one time. It's not possible, because you can't share the power back and forth. This is a really quick schematic of what channel looks like. You got a solar array, a regulator, switching unit, which allows you to take and bring on the paralleled battery charge discharge regulators, and then that goes through the primary switching network shown here. It feeds a set of DC to DC converter units, and the output of the DC to DC converter units are, in fact, the secondary system. If you want to parallel power from another power channel, you have to basically take and parallel the DDCUs into the secondary in order to make that happen. Now, we had a number of design challenges. Once again, a view from the big 80s. We started out, we were building a 75 kilowatt station from the very beginning, and that was 10 times greater than a typical satellite at that time. And it forced us to go to high voltage, 120 volts. The primary reason for that, by the way, was to get the mass out of there, which I think is fairly straightforward. But it generated a lot of questions that we really had to deal with. The first thing was, given the voltages and the currents, how do you safely interrupt? How do you basically interrupt the high currents and high voltages with spacecraft hardware and really have minimal impact on other loads? Which basically led us to the problem of, since we were dealing with high voltages, we had to figure out where the hell we were gonna acquire high voltage parts, especially high voltage semiconductors and high voltage capacitors that were high enough reliability to space. And in some cases, we actually had to develop new components, which is always a bad idea, by the way. Don't get into that. The other problem, if you remember the thing, we had the stability problem of multiple power converters acting in parallel, and then finally we had the problem of spacecraft charging, which we didn't, because of the high voltage solar arrays. You could basically charge the surface of you could basically charge the structure of the station, and that gives you which would be very dangerous for the astronauts. Okay, I finally got it to move. Okay, so what were the reliability challenges? Well, in any system that you have, you want to deliver a low mass system. Okay, and that's true with any space vehicle that you build. But in order to do that, a lot of the things that you need to address works against you being able to deliver a low mass system, which is, once again, we've talked a lot about the cosmic and solar radiation, both total dose and SEE, the fact that you're dealing with vacuum operation and constant thermal cycling, launch vibration, and even the problem of low pressure, where you could potentially get passion breakdown and corona within the ORUs. So what did we do on trying to meet these challenges? Well, we basically wanted to incorporate selective redundancy wherever we could. Given that we've got 8 separate power channels, you've got selective redundancy within the system. We sort of backed into that. You got to incorporate radiation tolerant parts. You've got to derate the parts for things like voltage spikes and things like that to make sure that that fundamentally they're going to hopefully last. You perform, one of the things you do is you perform a lot of environmental testing, burn-in, thermal cycling, whatever, in order to assure that the things are functional. And in addition to that, we did a lot of subsystem and system testing. In fact, we did a lot of end-to-end system testing. And an interesting sidelight on that was that we wanted to do an end-to-end system test, and NASA headquarters fought us extensively on that. And they said that it wasn't necessary, we should buy off the risk, or we should just accept the risk, which was kind of interesting, because they were arguing this like about 6 months after it became obvious that the Hubble telescope didn't work. And the reason was because they didn't do end-to-end testing with the system to detect the mirror problem. We did do some analysis. I'm not going to go, since I'm kind of over time, I'm not going to go through all of this, but I did want to talk a little bid about the architecture reliability analysis, because Clay talked about this earlier. We did want to determine the failure rates on the orbital replacement units, and contrary to probably good practice today, we use the Mill Handbook 217, but our problem always was the specialized parts. They're always a challenge because you lack reliability data, and so the numbers that you come up with in the final answer, in the final analysis, in our case, we felt that what we can do is we can use the data to compare architectures in the design, but as far as the absolute reliability of that, because we had no data on the newer parts, we couldn't use it for design. We couldn't use it for any absolute numbers as far as reliability goes. In the past, I believe the ISS collects reliability data on all the ORUs, and they do a Bayesian update on that. I've used the data myself a number of years ago when we were doing technology roadmaps. I think they still do that. It would be interesting to take a look at that. I would have brought it with me, but it's ITAR restricted, and being retired, I don't even have a copy of it. So, takeaways. Space station power system development was a challenge because the current and voltage levels necessary to deliver the power. The reliability was achieved really by using multiple power channels with a complex interconnection system. And an analysis of absolute reliability was a challenge because many of the parts were unique, and the ORUs had no operational history. And so unfortunately I went over a couple minutes, but that's my story, and I'm sticking to
it. We appreciate it, Jim. Again, guys, put your questions in the Q&A if you have them, so we can get to those after everyone gets through their stuff at the panel. Thank you, Jim.
Sure.
Next we have up Tim Lawrence. So Tim is retired from NASA after 39 years of having served as a power system manager for the Gateway program, a power SIG co-lead for the Constellation program, and the ISS, oh, I have a hard time with this word every time I see it, tertiary power system manager that helped integrate portable loads and payloads to the ISS power system. After 1 year of retirement, he is now consulting for Lockheed Martin regarding the lunar power distribution. Are we ready? Oh, you're ready, Tim. So I'll hand it over to you.
Yeah, I did fail the NASA seminar on retirement, and so here I am. Why don't you go ahead to the next page, please? And what I'm going to do is I'm going to kind of tell you the story of several case examples that really happened, and let you know how reliability can be negatively affected by, negligent quality control and testing. Every large program that we've had both ground and on flight, on orbit failures. We had people killed on the ground during testing and, you know, uh, during the flights. And, every program documents these lessons learned, and they put them in the database, and it's for registered users. There's a lot of protected information in there, but those databases do exist. So it's always a great mining tool to go and learn what people have done in the past to try to help the future. Programs these years, they last decades, many years anyway. And there's losses of experienced personnel throughout those years. And as we get new quality control and test personnel, the integrated requirements may not be known by these people. And the previous knowledge, gained by their predecessors is lost. And especially in areas like testing procedures, test setup, equipment usage, test flight history, results, all that. So one cannot assume that reliability of parts will stay the same over time. Even similar or exact hardware design certs may change due to vendor processes, manufacturing changes, mission environments change, etc. And a case example is the orbiter had 8 SRB Inconel nuts. They're very large and very huge nuts that fit on these 8 flight bolts, launch bolts, down at the SRB skirt, 4 on each SRB. And it holds the entire shuttle to the pad. And for years, the primary and secondary pyros, they successfully cleaved all 8 nuts away from the threaded bolts, and any one of the 2 pyros in each of the nuts would be enough to cleave the nut away from the bolt. And years into the flight, unknown to NASA, the manufacturer decided to strengthen the Inconel material, make it better. Who would ever argue about, trying to make it better? Everybody wants it better. Well, what this did is this resulted in flights where the pyros, they failed to properly cleave the nuts away from the bolts, even though we fired both pyros, and even just one is normally what it would take to cleave the nut. Both of them firing together still didn't clear the thread, and we had partial engagement. And as we launched, we did some damage to the SRB skirt area, and that's almost a catastrophic loss of crew, vehicle, and the entire launch pad assets. And this is example of where quality control failed to maintain the critical explicit contractual materials performance throughout the contract life. And they also had a notification of change that they would notify NASA, and they failed to do that when they changed their materials. And subsequently, the manufacturer reimposed the original specifications and processes with a renewed emphasis on reporting. So next page, please. Okay, so, every program is going to streamline or cut tests, for cost, schedule, impact avoidance. It happens every time. There's good reasons for doing that streamlining test, and every time you cut test, hidden risk remain, unknown until flight, and failures can easily result in much more cost later to the program than the test that was cut to save cost up front. And those failures can result in program cancellation or loss of crew. So always use, previous lessons learned to justify testing, but also use cases where proper testing prevented flight failures. And a case example here is the SSRMS control workstation was not tested with a utility outlet panel prior to flight. As Jim just mentioned, we did a lot of things on ISS that were not end-to-end tested. And this is one of those items. The utility outlet panel, it's just a 120-volt DC wall plug that powers portable equipment. And the SSRMS control station, it's actually kind of a portable work control station that plugs into this wall plug. And this UOP has both AC and DC GFCI for shock hazard protection. So the UOP started experiencing in-flight power trip-offs when we plugged in these laptops that utilize data cables. And what it was happening was that these small non-hazardous AC, current stirring currents, and the power supplies were bypassing the UOP AC GFCI, and it was inadvertently tripping the shock hazard safety circuit. And so, this was investigated and corrected by starting to use some cables that had, double insulated grounds and all of this other stuff. But as we were coming up to the next flight, at this time, I was reviewing the ISS airlock delivery flight products about 1 month prior to launch. And I've noticed this control workstation never was tested with data cables, with UOP with active GFCI. And, we've had these on orbit trips, and I was like, oh my gosh, we're fixing to have a Hubble repeat. The Hubble was 10 years prior to this time. And so it was on everybody's mind. So we rushed to KSC to perform, tests with a CSA call unit. And we did dozens of tests. And sure enough, 99.9% of the time, the UOP GFCI immediately tripped upon power up of the control workstation. Well, that's going to be, pretty bad, because we needed this arm to pull the airlock out of the shuttle bay and attach it to the station. And so here we are, approximately 1 week before launch now. We're having to fabricate bypass cables. And we did that in 3 days, just 24 hours around the clock. And we put double grounds on them for safety. And then we put them in a T-38, and an astronaut flew them off to the Cape, where they were there was no place to put anything. So we literally taped them to the flight deck chair. I was told it was the commander's chair, but we taped it to the chair. So on that flight, when we launched, we didn't install these UOPs. There was just an empty hole in the wall. And instead, we put these bypass cables in that hole and plugged it directly into the UOP power feed cables, which then were subsequently plugged into the workstation. And
I do want
yes.
to do, we have about 1 more minute.
Oh, okay. And so the bottom line is that we were able to work and resolve that, and did the power cables with double grounds. So next page, please. Okay, and then we had the electrically erasable prom on orbit failures. This is where the EPROMs, they're used throughout everything, all the equipment. And in 2000, we started experiencing 3 times higher than expected rate of health flags. And we found out that many of these EPROMs were not tested properly by the manufacturer. The error correction code was not activated by the manufacturer and many of the EPROMs. And but we found out also that there was a way to rewrite the memory, the memory out of the SRAM into the EPROM, and refresh the cell charge and start working. And subsequently, we had to replace or refresh all of these EPROMs over the years, and that was a substantial impact. Another example was the UOP PCB board. those normally go through a 300-hour burn-in. We did that, but they were never really high-pot tested layer-to-layer leakage in the 7-layer board prior to flight. And that we started experiencing on-orbit failures, and we found out that there was lots of pre-preg issues. We brought one, fell down, did color x-rays of it. We had everything from flies, human air, metal flakes, etc., and all these voids and bent layer to layer metal layers. And what we had to do there is we took these boards, the PCBs that were not used yet, and we were still building UOPs, and we went through a PCB high pot test, layer to layer testing, and sure enough found a lot of problems in a lot of boards, and we screened those, used the ones that passed, and subsequently flying. So go next page, please. And the takeaway here, it's not just a reliability number assigned to equipment that means something. The proper quality control and method of test are critical, okay? And if performed improperly, reliability can be unreliable. Most important testing lesson learned of all time, as the Apollo astronauts and all the engineers said, test as you fly and fly as you test. Don't experiment if you can help it on flights. Let me introduce this last bullet by first giving a story. I made a promise to Chavla. Everybody just called her KC. She called me one evening while I was working outside at home, and she was crying, and I was like, oh my. So she told me that her flight had just been deferred yet again with a compartment leak, and a crew's devastated, and she jumped up on top of her desk at work and started shouting to all of her crew members, how cool it is we get to go into space. And after she did this, she was drained, and she called me crying. And, she just needs somebody to talk to. And I told her we got to protect her and everything. And, and as I watched her launch out into space, I told myself, how cool indeed, going into space. And, we all know the story. We lost KC and the crew on that mission. And, I made her a promise that, she asked me, if something happened to her, I would make a promise and try to keep space flight alive and not to let her death be in vain. So I tell all of you for KC, this last bullet, loss of mission equipment is bad. The loss of personal friends, it's absolutely devastating. This loss can happen during ground test. So I ask everybody as we go forward, design, build, test, and operate as if one of the most important persons you know of is on the mission. And from beginning to end, if you have a valid reason, to press for corrective action, do so. And if you're challenged, defend it with facts, not overbearing emotions, hold to the facts, and don't let intimidation suppress the reporting of those facts. So I ask each of you, for KC, keep space flight alive and think of how cool it is we get to go into space. And that was my little talk, and we'll move on.
Tim, thank you very much. We went over a little, but I think that last bullet was really important. So I wanted to make sure that you got to say that. Thank you very much.
You bet.
Our next speaker is Dr. Clay Smith. I think he was on earlier, but I'm going to do an intro just because you might have been just getting on and not heard it earlier. So Dr. Smith is a member of the principal professional staff here at APL with over 35 years of experience analyzing systems from risk, reliability, and safety perspectives. These systems, including NASA and DoD missions, payloads, ground communication systems, air traffic control systems, and mission systems. Dr. Smith is a reliability engineer lead for APL's space exploration sector. He created and managed NASA's International Space Station program probabilistic risk assessment, specifically geared toward quantifying the safety risk during operations. So, Clay, are you ready?
I am.
Okay.
Thank you, Jamie. So I was asked to give a little bit of discussion about the ISS PRA. So I'll preface this with my knowledge of the ISS PRA is 20 years old at this point. but I can give perspective on what we went through in order to develop it. But I don't say anything about what you're seeing here is the actual state of the current PRA. So take that with the intent it's given. I can change. There we go. So obviously we modeled power as well as all the other systems on the station. So we had a challenge on how to model power for the reasons that Roger talked about, that, you know, this is a 24-hour thing that's working. It's not a one-shot, push the button and it goes. So how do we do that? The other thing that we had a challenge with is that all the systems that we were modeling needed power. And so do you model within the other systems and say that power is needed for avionics to work, or do you completely separate it? So we had to do a mix of both. And the chart you're seeing here is what we created. We created many of these, but this was what at the system level. And down the side, you see the systems that if a system is lost, then how does it impact the other systems along the top? And what you'd expect going across is that if you lose power, whether it's US or Russian side, then you affect all the other systems, right? So that's not a surprise. But the other thing that we needed to take into account is that if you lose some of these other systems, you will lose power. So if you lose CNVH, for example, or if you lose propulsion, then power is affected. And so you get into the system, this paradigm of having your logic be in a loop of power system fails, thermal control fails, but thermal control fails, it fails power. So we had to wrestle with that. Part of what we did is to split power generation and power distribution. And as you saw from Jim's discussion, that power distribution is, you know, very, very complex switching system. So at the system level, we modeled and we went back down to the DSCU or the DC converters. Sorry. And then there was another modeling section for the power generation system. So that was one thing we had to wrestle with. The other thing we had to wrestle with is what dictates the initiating events for the PRA. What you're seeing here is basically, well, it is the master logic diagram for the station. So it has to maintain the crew health, and then it has to work as a machine. And then part of working as a machine, obviously, is power. So the reason I show that is this is the expanded view of that. These are all the initiating events that we were tracking for the space station. And specifically, we needed to have initiating events for power. You'll see that there are 3 initiating events for US power. So channel 2B, channel 4B, and a separate one for both failing. And the reason for this is that when we were modeling this early on, where the full 8 channels were not up, it wasn't fully connected. So the redundancy didn't actually exist. It could exist, but it needed an EVA to put in a jumper outside. So it was, you know, there was a question earlier about maintenance as part of these models. And so this is, you know, one of the places where that starts to show up. And then common cause or failures that would take out both channels at the same time is modeled separately. This is what one of those power channel scenarios look like. And I know it's a bit of an eye chart, but a couple of things just at a high level I want to point out. First one, that green bubble is essentially a fault tree for how power generation of one channel can fail. And then we ask a bunch of questions on can it be fixed or repaired? And that has to do with EDAs to fix it. And if it can't get fixed, then there's this place where we can put a jumper in to bring in the other power channel. The next questions are, does this redundant system work? In this case, channel 4B. And it comes up in a couple of places. One, is the jumper successful? And that's one answer. And then the other one is if it's not successful. And then what happens? And then the other part is, can the rest of the station survive given this failure? And given this failure and the backup redundant channel is working and doing what it's supposed to do. So all of these things put together are how we were modeling power early on. Now, as the system expanded and you had all of the power channels available, then these kinds of things started to simplify a little bit. And you, as Jim pointed out, there's more and more redundancy. So quick, just kind of challenges and kinds of things that we talked about when we were doing the modeling of the ISS PRA. And take questions that we discussion.
Thank you, Clay. All right, last but not least, we have Ron Galvad. So Ron has worked at the Johnson Space Center for 35 years, 15 years working for Space Shuttle Electrical Power Distribution and Control, and 16 years in counting for working ISS Electrical Power System. He worked on the development of the station. Ooh, I'm reading too fast. Station Shuttle Power Transfer System, SSPTS, which permitted the shuttle to spend longer time on orbit during ISS assembly flights. He was also involved in the lithium-ion battery development project, which replaced the original NIH-2 batteries on the ISS battery storage system. Ron, are you ready?
I am. Can you hear me?
I can hear you. Are we driving your slides or are you driving?
I am trying to share right now. So I clicked on Window, Microsoft PowerPoint share, and it is not sharing.
Are you clicking on share screen on the Zoom link?
Yes.
Does a pop-up come up and ask you what screen you need to share?
It does. And I'm trying to click. It says,
oh,
there it is.
There we go.
All right.
This is me sharing your slides. We'll just
Well,
roll this way.
Great timing. Okay, well, we'll go that route then. Next page is just I guess the intro, and then we'll go to the next one. So basically, it's just an overview of what the EPS system is, and Jim went with a little bit about this on the specifications in terms of how much the arrays when they were new and so forth. And then the system as such obviously cannot support all the power from the arrays, even at the beginning of life, because for multiple operational constraints. But in any case, this is kind of the overall specifications of the system. Next slide. So the core functions of the EPS obviously generate, store, distribute, and convert. And then the secondaries, which is obviously thermal control of the EPS components, the grounding. And then of course, EPS handles all the lighting, both internal and external to the vehicle, in addition to the emergency lighting, which we removed a few years back due to maintenance requirements and basically replaced them with stickies. Next slide, please. So this kind of gives you an idea that APS it's a big deal. So when you see box diagrams or schematic, it shows like a few boxes and this is the EPS. But really, this truly is the EPS. It's a lot of equipment, and basically we touch everybody for obvious reasons. And so it's a system that we have to maintain a level of robustness and compatibility with a lot of loads. And we do that multiple ways due to either testing, doing power quality testing, providing requirements that show the compatibility between sources and loads, and then we do analytical system level analysis. Since we don't have an on the ground power system that has all the loads, we have the infrastructure, then we have to mimic what those loads are, and we do that through an electrical model. Next slide. So this is basically a little more detail in terms of what the EPS system is. So I'm going from left to right. On the left is really the what we call the primary system. You have the batteries going to the battery charge discharge units on the top, then going to the box that basically brings all together. That's the DCSU, or the DC switching unit. And so it brings power from the batteries when you're in eclipse, and then power from the solar array, which is on the bottom, through the sequential shunt unit, which is basically the converter box that tells the system, I need you to be at a certain level. Then all those flow from left to right to what's called a main bus switching unit. And this basically is where all the power comes into the station from all 8 channels. And so they're concentrated right in the middle of the vehicle. And this is where we have or close to it, where we have our primary single point ground. We also have the capability of tying channels together. So if you were to have a power channel down, what you do is you end up tying it to a channel that's active. And we do that either through operational issues that we may have or due to failures. And then from the MBSU, you're still at the primary voltage, which is anywhere from 130 to 177. It goes now to the DC to DC converter unit. This is really where all the, I guess, one of the most complex boxes. This is what converts from a coarsely regulated primary bus to a very tightly regulated secondary bus. And the requirement is very tight. It's 124.5 plus or minus 1.5 volts. And a few years back, we actually did we did some data gathering, and we saw that the regulation was even tighter, closer to like 0.6 from that middle point. So it's a very tightly regulated bus. And then from there, you're basically going downstream. The SPDA, RPDA is a big fancy name for saying switches. So that's where we have all what we call the remote power controllers, or our electronic switches. Basically, they're on off, and they either have current limit capability or non-current limiting capability. And from there, you then go to the loads. I kind of pointed there towards the bottom in what appears to be orange, the issue that Tim pointed out in his charts with the UOP. The UOP basically had a ground fault circuit interrupter, kind of like what you have in your bathroom. And basically it was tripping, like Tim pointed out. And essentially what happens is there was a lot of equipment that had leakage in excess of the requirement. And so a great safety function ended up being detrimental to the point that it became unusable. And so what we ended up having to go in and actually clip the circuit out. So no UOPs on station have this GFCI function anymore. So this is kind of the overall structure. When it comes in terms of reliability, one of the key things I'm going to point out is, as you can see in the bottom part in bolded in black, it says SSP 5251, user electrical power specification and standard. Basically, that is the requirement that says for you to tie into the EPS system, you better meet these requirements. And so it is key. And the reason it is if you start putting loads that are not within these envelopes that we put in, you can essentially make the system unstable, and as such, it becomes unusable. So one of the key things, obviously, is to have crisp requirements for whatever's going to be tied to the EPS system. Now, in the beginning of the program says basically, hey, we're going to have all these critical loads, kind of like the computers, the gyros, I mean, all the important stuff that you need to have, the ECLIS system, the active thermal. Yeah, those are core systems that have a very rigorous development program, and very strict requirements in terms of testing, because for obvious reason, it's needed for the operational health of the ISS. And then they said, hey, this is a laboratory. We want to have all these loads, but we don't want to have that rigor on these loads because that costs money. And the point is to be able to have this laboratory that everybody can use. So powers to be decided we're going to set a different set of requirements for these payloads and make it less rigor. And we're going to allocate them to a specific source. So in the middle of the page, you'll see DDCU. We had dedicated DDCUs to what we would call payloads at the time with a different set of requirements. So as station grew, we ran out of the capability of just using these very unique, I think it was 4 of them. We were growing and we needed to have more capability. And at that point, these payloads started migrating to channels that actually had critical functions. And so you can see where that is becoming a recipe for disaster, because you're having 2 set of requirements for loads, and yet you're putting it on the same converter. The converter can't differentiate between powering a critical load or powering a crappy load. And so the rigor then came back, and we basically had to institute hey, you need to have the same set of requirements for anything. And so it was a little bit of an uphill battle, but we got to a point where they understood that this is what we need for everybody to be able to have proper power quality in terms of what they need to be able to function. One of the things, and I'm going over some of the questions that I was sent, the pre-prepared question is, were there any things that events unanticipated the power system handled well in spite of unknown unknowns? And the answer is yes. Unfortunately, we ended up having manufacturing defects. Now, obviously, I'm going to state the obvious. You have to have a rigorous program in terms of your components. But yet the things still fall through the cracks. And so we had a manufacturing defect on the workhorse of our switch gear, which is the RPC. And essentially we had a gate oxide issue with one of the FETs. And basically what that ended up doing was fooling the RPC, the electronic switch, to think it was in current limiting, and it just tripped off. So out of nowhere, all of a sudden, a load loses power. And so there's no overcurrent, there's no indication of anything other than it just stopped working. And so 20 years into the program, we still live with that issue. Now, over the years, we've managed to obviously correct that issue with a new lot. And then we eventually have to start bringing them down to fix them on the ground, and then obviously flying back up. So again, manufacturing issues is a way of getting a reduction in your reliability. One of the other thing is improper testing, like Tim pointed out on the EE proms. EE proms was a big deal, and to a certain extent, it still is. Not as bad as before, but one of the things we had was if you had enough of these EPROMs with no error correction code enabled, basically we're having bit flips, and all of a sudden we get a bit flip and we look into the location of memory. What happened? What is it doing? And we got to a point where you had enough bit flips that you got into the area of memory that basically stopped communicating with us. So we had a box, in this case the MBSU on the left-hand side, that basically it's a big deal. It had one EEPROM for this huge box that controls 2 power channels, and it stopped talking to us. So you couldn't command it, the switches to open, to close. You couldn't do anything with it. And so at some point, 2 of those boxes, there's 4 of them, that's 4 power channels affected, had an issue that we could not communicate with the box, all because of the EEPROM issues. So again, those are kind of examples of things that we have experienced that I'm not sure how you not look into it, but again, it's looking back in hindsight. Yeah, obviously I don't want to manufacture an issue. Yeah, obviously I want error correction code. Yeah, I want to make sure that I do enough read writes, that I validate the components, but ultimately your test plan has got to be enough that will weed these things out. So anyhow.
We have about 1 more minute.
Yep. So I'm pretty much done. I can go maybe one more chart, maybe one or two. So this is just how we built it. And if you go one more, let's see, go one more chart, storage, another one. So this is just showing what they are, where they're at. And I can keep going for a few more charts, just kind of give you an idea what we ended up. So this is how it's kind of put together, where things are located. Next chart. This is as we were building it. Jim mentioned that a lot of the fact that we have the 8 power channels gives us enough capability to handle, issues. When we were building it, we only had 2, and we ended up having what's called a power on reset, and that took half the station power because there's 2 channels, one of them POR'd. So that was a big deal. So things like these are the things that we encountered while we're assembling it. Next page. Then the MBSUs came up. Keep going. And so when the MBSUs went up, that's when we had the double EEPROM issue the first time it showed up. So this is what the MBSU does. As you can see, there's 4 of them. Each one handles 2 power channels, so that's a total of 8. Long story short, when it stopped communicating with us, the top right-hand side has MBSU 1. We had to go R&R. At that time, we had already had 1 power channel down. So we were basically at one point 3 power channels down. The original one that was down, which was 3A, and then MBSU 1 was going to be R&R. And as luck would have it, we removed the one that had failed. And when we tried to replace it, it wouldn't go in. So there was quite a while where we're down 3 power channels out of 8, and we were still able to manage. But then we started finding other issues like, hey, when you have 3 power channels down, all the other loads have to go somewhere. And so we found out there may be an issue called cascading failures, meaning, you're overloading the other channels as all this is happening. So things that normally I don't think were envisioned, things that we were able to encounter, and things that we were able to deal with. The only thing I'm going to touch on here, because again, I'm looking at the questions, if you could design an ISS 2.0 from the ground, are there any changes you would make to the architecture? Absolutely. And one is you need to have some sort of high-speed instrumentation on the system, because to this day, anytime something happens, we cannot, the instrumentation currently that downloaded, it's so slow because it's intended to be quiescent. It's kind of give you a health of the system. It's not intended to show transients or things that you would be able to capture in a lab environment. So if you were to have an internal, a system that just basically gets some of these parameters, even if you're just downloading it to a local drive or a system, at some point, if you have an issue, then you could potentially just look back on it and try to understand, rather than what we have to do, which is we have to bring down the hardware because we can't troubleshoot it on orbit. The instrumentation on board is way too slow. So I have other, but I think I'm over. But that was my biggest, one of the things that I would make sure that it was in my system or in the design to accommodate some sort of high level or a high speed instrumentation that can give you some troubleshooting help and not speculate what we've done multiple times. So that's my story, and thank you for your time.
Thank you, Ron. It looks like we do have a question in the chat. So the question here is, what drove the discussion for the specific value of about 4 kilowatt hour of battery energy storage aboard ISS? Just power needs of a few subsystems during eclipse? Or was this number ever contentious, or was it straightforward call?
You're talking about the original specification, or I'm sorry, I didn't catch
the first part. It says, what drove the decision for the specific value of about 4 kilowatt? Battery energy storage aboard ISS.
So the requirement for the energy storage for each battery, and 4 kilowatts is not the right number, by the way, but the nickel hydrogens were basically two boxes, and they had and the energy storage at that time was in terms of amp hours, which was 81 amp hours. And so that was a function of the need to what the array had. And I assume, and again, I would have to defer to Jim on this one, but the amount of energy for each system would have had to be determined in terms of what the capability that you had in the source versus how much you could distribute and account for the different modalities. Because even if you can generate 30 kilowatts on the array, you cannot distribute 30 kilowatts through Eclipse because there's limitations on the hardware, on the chargers, and then the operational constraints that if one of your boxes goes down, you don't want all three of them to trip. So the requirement, the original requirement had to be specified in terms of this is what we think we need for each power channel. When we did the lithium ion batteries, we actually took the attack of, hey, it has to be a box that's got to be form, fit, and function like the nickel hydrogen. So we took whatever area that was in and wedged the biggest battery cell that we could put in there, which was 134 amp hour batteries, and gave station basically more capability at that point, even though you can't technically use all of it because again of operational constraints in terms of how you operate the 3 BCDUs per channel, because you have to account for the fact that one may go down and you don't want the other ones to trip because of an overload. So that's basically trade-off studies that were done originally, but the lithium ion was a function of what space we had and how much energy we can.
Jim, did you
Jamie?
want to chime in? I know he referred to you. on that.
Jamie, can you hear me?
A little bit. You're a little faint.
How about now?
That's better.
Is that better?
Yes.
Oh, okay. I think the answer actually is actually simpler, if you believe it or not. What happened was that the number 75 kilowatts, I think, was actually almost picked out of thin air back in the early 1980s as what we needed for the space station. I don't know that there was a whole lot of analysis that went into that. And so as the architecture of the system evolved, okay, and it evolved over a number of generations. We went from a 20 kilohertz system to at one point we actually had baselined a 400 hertz system, 3-phase AC, to a DC system. And then we looked at what the capability of the switching hardware was. We came up with the architecture that exists. And when you look at each of the individual power channels, you want a balanced system. In other words, you want the thing to be able to deliver as much power in Eclipse as it does in installation. And so when you go back and you run through all these numbers and you look at what the amount of energy storage that you needed for that channel at that time, what you did is and you come up with the amount of storage, and you look at what the size of the nickel hydrogen batteries had to be. It basically sized the batteries out to 4 kilowatts.
Okay, thank you. And I need to apologize to Perry because I missed the first question and jumped to the second one. So another question for the panel is, does the ISS power system include current sensing circuit breakers? Do you have reliability issues with circuit breakers? Let's jump on that one.
So circuit breakers, and so an electronic circuit breaker, right? Because we don't use thermal breakers in our EPS system. But the question being is, do you have reliability issues? Again, it goes back to what I talked about, the FET controller hybrid. That's all the current limiting RPCs on station have this hybrid circuit that has an issue. And so the issue has never been the tripping function in terms of it's a safety switch, right? It current limits and trip. That has never been an issue. The issue is it trips autonomously for no reason other than the fact that it has this defect on the current level detector. So that's where the reliability issue comes in, because you could potentially lose that load if you can't recover it.
One thing I could add there, Ron, this is Tim, is We have and always have had issues with payloads and other utility type loads surpassing their inrush and surge requirements, which then would trip the electronic circuit breakers, the RPCs. And out of all the lessons learned of passing down what requirements need to go to the payloads and everything, it's usually that inrush and surge that these loads experience, usually on turn on and stuff like that, that would trip our breakers, that would give us a lot of problems in testing, and they would always do waivers against it and then fly these, and then we would end up, having some trips and things on orbit. So it's imperative that we build our EPS system utility grade to be able to handle these typical inrush and surge requirements.
We have two more questions in the Q&A, but I think our time is coming to an end. So if you guys could go in and answer these questions, I don't know if you can see them, but you get to them and you can type your answer in there if you want to make sure those get answered. But I think I need to hand it back over to Matt. I want to thank the panel. That was really, I'm a radiation effects engineer, so we touch reliability a little bit. And so it was kind of really exciting to hear a lot of things you guys talked about today.